Well, good evening, sir. I
Uh,
can say good evening.
Good evening, sir.
Just 5 to 10 minutes, sir. Once the
No,
participant has, we will start, sir.
no problem, sir. In the moment,
Ah,
shall I share the screen? I can screen and check the video screen.
sure, sir. No problem. No problem.
Yeah, I need host disabled attendee screen. Yeah, for me to share the screen, permission is needed.
Okay. Okay.
Yeah, got
Yes,
it.
sir.
Now got it, sir.
Okay, sir. Then no.
Okay. Are you able to? Hello. Hello, Deepak. Hello. Hello, Deepak. Hello. Hello.
Yes, sir.
Madam, my screen, I'm unable to slide sharing. I'm
No,
capturing.
sir.
Is it visible? My slide is visible.
No, sir.
Yeah, that's why, madam, some problem. Can you share my slide from there? Yeah, it's coming and
Just a minute, sir.
it's coming and going. You should give permission or anything. Slide sharing, it will come there and is going. Slide sharing. It's coming and going, madam. Yeah, when I select window, screen window will come. You have to permit there, or you have to slide. You have to run the slides. Yeah, entire window I selected. Entire screen I selected.
Sir, your screen is not visible, sir. Not
Sir,
shared. So
yeah,
there,
that no, sir. I'm able to share, but sharing it will come immediately. Your window is selecting. Select window for sharing the type I have selected. I selected. I selected the slide and its window. That's all, sir.
yes.
Yeah, what is coming, sir?
So nothing, sir. It
Yeah,
will
that's
going to
why.
display only the.
Yeah, that's why from there only you can.
There, sir.
Huh?
Is it there, sir?
ಸುಧನ್ ಸರ್ ಹೇಳಿ.
Is it possible to share the PPT there itself?
ಕಳ್ಸಿದ್ದೀನಿ ಅಲ್ಲಿ ಇವರಿಗೆ ರಾಜೇಶ್ವರಿ ಅವ್ರಿಗೆ ಕಳ್ಸಿದ್ದೀನಿ. ಇಲ್ಲಿ ಸ್ಕ್ರೀನ್ ಅಲ್ಲಿ ಸೆಲೆಕ್ಷನ್
Sorry,
ಆಗ್ತಾ
madam. Please share the slide to Devraj, sir. Rajeshwari, madam.
ಅಥವಾ ಪರ್ಮಿಷನ್ಸ್ ಏನಾರ ನೋಡಿ ಅಲ್ಲಿ ಪರ್ಮಿಷನ್ಸ್ ಏನಾದ್ರು ಕೊಡೋದಿದ್ರೆ
ಸುಧನ್
ಕೊಡಿ.
ಸರ್
Sir,
ಸುಧನ್
sir.
ಸರ್ ಕೋಸ್ಟ್ ಆಗಿದ್ರೆ ಶೇರ್ ಮಾಡ್ಬೋದು.
ಅದೇ ಅದು ಎಕ್ಸಿಟ್ ಆಗ್ತಿದೆ ಶೇರ್ ಮಾಡಕ್ಕೆ ಅದು ಎಕ್ಸಿಟ್
ಶೇರ್
ಆಗ್ತಿದೆ.
ಮಾಡಕ್ ಹೋದ್ರೆ ಎಕ್ಸಿಟ್ ಆಗ್ತಿದೆ ಸರ್. ಇಲ್ಲಿ ನಿಮ್ದು ವಿಂಡೋ ಮಾತ್ರ ಸೆಲೆಕ್ಷನ್ ಆಗ್ತಿದೆ. ಎಂಟೈರ್ ಸ್ಕ್ರೀನ್ ತಗೊಂಡಿದ್ದೀನಿ, ವಿಂಡೋ ತಗೊಂಡಿದ್ದೀನಿ. ಈಗ ಬಂದಿದೆ ನೋಡಿ ವಿಂಡೋ. ಈಗ ಬರ್ತಾ ಇದೆ. ಈಗ ಕೊಟ್ಟಿ ಈಗ
Yes, sir.
ಬಂದಿದೆ.
Now it's
ಈಗ ಡಿಸ್ಪ್ಲೇ
okay.
ಆಗ್ತಿದೆ ಸರ್, ಬರ್ತಾ ಇದೆ.
Now it came, sir. You have given a co-host, so it has given. Now it's
Just
coming.
maximize the screen.
Maximum. Just a moment. Yes, sir.
F5.
Yeah.
If you press F5, it will come.
Yeah. Are you able to see it?
ಎಸ್ ಸರ್,
Are you?
ವಿಸಿಬಲ್.
Yes, sir.
Yes,
That's
sir.
all. Yes, sir. Yeah,
Please
that's all,
make some
sir.
maximize, sir.
That's the maximum, sir. That's the maximum. This is the maximum. Are you able to see this? Full screen I have given.
Full screen.
Yes,
So please
sir.
press F.
Yes, it's coming.
No, it's exit.
Yeah, just now I exited. Yeah, one more time
Okay.
I'll share. Yeah, I exited only. One more time
Please share one more time, sir.
Yes, yes, sir. Yes, sir. From the beginning. Can you see the full screen now?
Yes, sir. Sir, please press F5.
Yes,
Yeah.
sir.
Yeah, it's full screen only, sir. It's in full screen.
This is full screen, huh? Okay, sir.
Yeah.
No problem.
Is it coming?
Yes, sir.
It is coming.
Yes, sir.
Full screen. It is coming full screen.
It's not display full screen, sir.
Yeah, that's why you display from there only, sir. Because here the option is that's all. See, slides is showing said from the beginning. Current slide speaker slideshow. I have taken the slideshow, and from the current slide or from the beginning. That's why you, madam, Rajeshwari, madam, you are having the slides. You display, madam, from there if you want.
Yes, sir. Yes, sir. Yes, sir. Yes, sir.
Yeah, better you can display. Is it full screen? You are going to display it.
Rajeshwari, madam, try once.
Yeah, if
Try
you
to
are
share
able,
the screen.
yeah.
No, sir. It's voice break. One ನಿಮಿಷ, sir.
ಮೇಡಮ್ ನೀವೇ ನನ್ನ ಹತ್ರ ಇಷ್ಟೇ ಬರ್ತಿರೋದು ಮೇಡಮ್. ಫುಲ್ ಶೇರ್ ಸ್ಕ್ರೀನ್ ಇದೆ, ಒಂದು ವಿಂಡೋ ಓಪನ್ ಆಗಿದೆ. ಅದು ಓಪನ್ ಮಾಡಿದ್ರೆ ಡೈರೆಕ್ಟ್ ಆಗಿ ಐ ಗಿವನ್ ದ ಫುಲ್ ಸ್ಕ್ರೀನ್. It's coming like that. That's all. That's what it's. ಅದಕ್ಕೆ ನೀವೇನಾದರೂ ಮಾಡೋದಿದ್ರೆ ಅಲ್ಲಿಂದ if you want to.
Sudan sir, it's enough, Sudan sir.
Okay, madam. Then no problem. Sir, shall we start?
Sir,
Is it full screen? Is it full screen?
sir, can you click the slideshow?
Yeah, I have clicked, sir. There is one slideshow as well as F5, not more than that. Now I came with
Okay.
XK.
In the top menu,
Yeah,
it's not working.
yeah, slideshow is there from the beginning. That's what, or else F5 is there. Full screen, it is coming to me from there. That's what's coming, sir.
Okay.
Yeah,
Sir, in
now
bottom there is an yellow button, is there, right?
yellow
Please click
button
on.
is there. Yes, yellow button is there. Start from the
Sorry,
current.
orange or something. You just click on, sir.
Yes, sir. I click on it. Is yes, click. It is clicked.
Okay,
Yellow
sir.
button is. Is it full
Uh,
screen?
little bit okay, sir.
Yeah, that's what I have done, sir. Sir, F5 is there or start the slideshow is there. These are the two things it can be operated. You told F5. You told the short button. That also I done it. You
Okay,
want you
sir, no
want
problem.
you want me
No, it's okay. No, no, no. Too much of zoom is there.
yeah, that's
Just
why.
please.
Now is this
Now,
okay?
okay, sir. Now, okay.
Is this okay? It is showing 72% from here. I have made it. Now
Yes,
I'll
sir.
go for
Now, okay,
now.
no problem.
See check the slides. Now you check the slides, sir. Now you check it.
Yes, sir, no problem. Now it's
Is
okay.
it okay?
Yes, sir. No, now it's okay, sir. No problem.
Is this visible? Second slide is visible.
So move to the next slide.
Yeah, visible.
No, sir. Only first slide is visible. It display only first slide.
Sir, Rakesh sir,
Yes, sir.
ಇದು WPS ಓಪನ್ ಆಗಿದೆ ಅಥವಾ MS ಆಫೀಸ್ ಓಪನ್ ಇದೆ ಸರ್?
WPS.
So can you open it MS ಆಫೀಸ್?
Sir, MS Office ಇಲ್ಲ WPS ಇದೆ ಸರ್ ಇಲ್ಲಿ.
ಹೌದಾ? MS ಆಫೀಸ್
ಅದು
ಆದ್ರೆ ಕರೆಕ್ಟ್ ಆಗಿ ಡಿಸ್ಪ್ಲೇ ಆಗ್ತಿತ್ತು ಅನ್ಸುತ್ತೆ.
ಇಟ್ಸ್ ಇನ್ WPS. ಅದಕ್ಕೆ ನೀವು ಅಲ್ಲಿಂದ ಮಾಡ್ಬಿಡಿ ಸರ್. ನೀವು ಅಲ್ಲಿಂದ ಮಾಡ್ಬಿಡಿ.
ಓಕೆ ಸರ್, ಗ್ಯಾಸ್ ಒನ್ಸ್.
ಅದಕ್ಕೆ ರಾಜೇಶ್ವರಿ ಮೇಡಮ್ ಹತ್ರ ಇದೆ. ಇನ್ನೊಬ್ರಿಗೆ ಕಳ್ಸಿದ್ರು ಕಳ್ಸಿನಿ. ದಟ್ಸ್ ವೈ ಯು ಕ್ಯಾನ್ ಡಿಸ್ಪ್ಲೇ ಫ್ರಮ್ ದೇರ್ ಇಟ್ ಸೆಲ್ಫ್.
ಓಕೆ ಓಕೆ ಸರ್.
ಹಾ. You want me to change the computer?
So just 5 minutes, sir. I will inform.
Okay, sir.
Rakesh sir. Hello. Rakesh sir, shall we start? Hello. Hello.
Hello.
Rakesh sir, shall we start?
Yeah. You are going to you are run the slides.
No, sir. You only share that one.
Yeah. Is it visible?
No problem, sir. You just share it. It's
Okay.
visible. Good evening, everyone. I extended a warm welcome to all the faculty members and participants gathered here today. We are here for this special session on quantum sensor and Industry 4.0 integration, which will be surely enrich our knowledge and inspire us. Now, it is my privilege to introduce our esteemed resource person, Dr. Rakesh L. Rakesh L is the Chief Technology Officer of ADA Lowless Software Private Limited and Vice Chairperson for Capacity Building and Education at the International Telecommunication Union. He is an AI researcher, cybersecurity specialist, and academic leader with more than 18 years of experience in software development, product engineering. He holds a PhD in computer science and postdoctoral fellowship from NIT, master in software engineer, and bachelor's in electronics and communication engineer. Dr. Rakesh L has been a mentor at ITU Women's in Cyber program from 2022 to 2023 and the Indo-Dutch Cybersecurity School in 2022. He has represented India as a delegate at the United Office on Drugs and Crime, contributed to Indopol AI for Law Enforcement program held in Singapore 2019, where he received an International Achievement Award. He has organized and spoken at World Summit on the Information Society Forum in Geneva from 2018 to 23 and was nominated for WSIS Prize in 2021 for project in healthcare and special education. His contribution extended to smart cities, digital inclusion, and global ICT policies, and he has actively participated in discussion with World Bank, IMF, Asia Development Bank, and ITU. Dr. Rakesh L is also a cyber awareness supporter. He has published research with the ITU on ICT, intellectual property, and e-learning for SDG. This is about a brief introduction about Dr. Rakesh L, and I have shared just a few points about Dr. Rakesh L because of the time limit. If I were to mention all the achievement, it could be needed at least an half an hour, sir. Sorry for this, sir.
Yeah, it's okay. It's okay. No problem, Phil. Yeah. How is the
And now I
slide?
would like to invite Dr. Rakesh L to take over the session and share his valuable insight with us, sir. Sir, please take.
Yeah. Thank you very much. Is my slides visible now?
Yes, sir.
Yeah.
It's visible, sir.
Is it in full view?
Yes, sir. No problem.
Yeah. Yeah, that's what. Yeah, because audience may not feel later. That's why. Yeah. Yeah. Okay, sir. Yeah, I'm Dr. Rakesh, director of the ATAL Software Private Limited, and we are basically into assistive technology and artificial intelligence, and also we have some of the work with related to quantum computing, particularly related to the arena. In the case of there is a smart weather system is there, where initially we are going to test those sensors, particularly in terms of simulation, and also we want to integrate it to the hardware later stages. Yeah, quantum computing, it's a very good platform, and to address the esteemed faculty members and also the guests, and my talk is related to quantum computing, in particular quantum sensors and industry 4.0 integration. Is that audible? Is it proper, Deepak? Hello.
Yes, sir.
Yeah. Is it proper?
Sir, no problem.
Yes, yeah, quantum computing, sensors and Industry 4.0 integration, exploring the revolutionary convergence of quantum technologies in modern industrial applications. As you see that the quantum, when you talk about quantum revolution, it's all about transforming the industrial paradigm. That's there is a what you call it as a we stand at the edge of the cliff of a new technological revolution that promises and fundamentally reshape the industrial process. And quantum, when you talk about computing, since from the last 3 days, we are consistently talking about the fundamental basic unit of information, and that is called as qubits. Basically, qubit is a basic unit of information. That's the point we need to start with, and also the fundamental properties of quantum computing. We are all familiar with two fundamental, two to three, but two at most fundamental properties: the superposition and entanglement. The quantum computing represents a paradigm shift from the classical binary computation to the binary computation, and leveraging the fundamental principles, superposition and entanglement, to solve the unimaginable and intraceable problems, which the classical computing has limitations. And sensors plays a critical role here. When you talk about quantum sensors, the sensing capabilities will be the highest, and we concentrate on unprecedented precision. Whenever we talk about a sensor, precision and sensitivity, these are the two primary points when we talk about sensors. And sensors are the starting point for any of the transformation of physical entities to the electric signals, and then the procedure starts. Sensing capabilities here in quantum, it takes advantages of the computational power, and the sensing capabilities will be beyond unprecedented precision. And we look into that, what is that unprecedented precision, enabling, because we call it as an unprecedented precision here, enabling the measurements at the atomic level. When integrated with the Industry 4.0, these technologies will have an synergic effect that amplify manufacturing efficiency, quality control, predictive maintenance capabilities. That is the amplifying the AI, that is the quantum AI, what we call it as a quantum AI capabilities. The convergence of these quantum technologies with the smart manufacturing that represents the next frontier in industrial revolution, promising the exponential improvements, processing, maybe a processing speed, or a measurement accuracy in the measurement, or system optimization. In all put together, the science of really small. That's the quantum mechanics. Why you need this? Why you need this quantum computing? The science of really small quantum mechanics. That's what we there is a technological, there is a paradigm shift, and there is a, as we are standing at the percepts of the technological revolution, the edge of the technological revolution, like what happened in our earlier days. You started from the Stone Age to industrial age to the next revolution of IT, and next, as the expectation of the human expectation, human capabilities increases, its needs as well as its wants also, means in terms of digital comforts is also essential. In order to cater that needs, we need a technological revolution, again and over again and again. The science of really small, that's the quantum mechanics, and the changing the technological landscape is a very interesting concept. And as you know that let's move into the fundamental quantum of foundation principles, that is the superposition. Qubit, as we mentioned, that qubit is a basic unit of information. And why this quantum computing is powerful? Because it has a multiple states, not only 0 and 1, or it has also more than that. That is, it can be in a both form. That's the differentiator. And suppose, say, superposition principle, like, say, make certain type of calculation faster. That is, when you are able to have a quantum multiple states, these qubits can exist in the multiple states simultaneously. The superposition enables quantum computer to process vast amount of information in parallelism, providing exponential computational advantages for specific problem cases. Let's let's think of a coin spinning, flipping a coin in the air. It's both head and tail until it lands. This is until it lands. That's the superposition principle. And another one more weird principle that is related to qubits is the entanglement. That is, suppose say we have simple notation. Let us presume that there are two balls. One is a red ball and another one is a blue ball. They are in different boxes and they are miles apart, and they are linked. There is a linkage. When we are able to open a box, when we identify there is a red ball, we are able to tell that in a very simple conventional method. When we are able to say that there is a blue ball is in the other box, there is a linkage or an invisible strength. That invisible strength which the impact of one will have an impact of the other. That enables computers to perform complex calculation by correlating information across multiple qubits, creating computational pathways. Two qubits become linked, and whatever happens to one instantly happens to the other, even if they are miles apart. There is an invisible strength. The two things are connected in a way that their states are linked, even if they are separated by a huge distance. This we have discussed already, and there are different methods to put in a simpler manner, because as we on progresses, we become more progresses with this session from last 3 days. We will become more what you call more acquaintance with these things. And also the quantum interference, which is again another property which we need it for future discussions, because when we come into sensing as well as the precision, this quantum interference plays a critical role. And suppose let we have a waveform interference. When you throw a pebbles in a pond, ripples from each pebble will spread out and interact each other. Some place they add up to create a bigger wave or cancel each other. Other leveling behind water, other leaving behind the water flat. For example, in our primary school days, we have come across light acts like a wave and create interference pattern in a famous double slit experiment, which we have played during our primary classes. That simple phenomenon, that simple form of interference, a simple form of interference pattern. What I mean to say here is quantum interference. Yeah, quantum algorithms manipulate probability amplitudes to constructively interfere correct answers while destructively interfere incorrect ones. That means to say that this process allows quantum computer to amplify the desired outcomes while suppress the unwanted results. This classical property of interference, which is based upon coherence and
Yes, sir.
decoherence,
Sorry
is
for disturbance. Sir,
yes,
your slide is not get moved, sir.
yeah.
Only
I'm just talking about quantum interference only. Now I'm going to the next slide. Yes. Now are you able to see the next slide? Are you able to see the next slide?
no, sir.
Yeah, I have moved the
Oh,
slide.
shall I slideshow from my end, sir?
Yeah, that's what I told you. You can
Okay,
show this.
okay,
Yeah,
Please,
you
sir,
can.
it's better to
I
share
will,
your
I will
screen.
do, I will do, sir. I will do. Okay, fine.
Yeah, yeah, you can do it. Yes, I'm available here. Yes, Sridhar, do you want me to send? Yes, sir.
Sir, 1 minute. I'm doing. Yeah.
Yeah, I'm sending you the document. If you want, I'm sharing the document here. Yes, yes, I'm sharing the document to you. Yes, Sridhar, I sent the PPT also to you.
Sir, yes, sir. I had 1 minute.
Yeah, you had
Sir, just 2
PDF.
minutes.
Yes, sir. Yes, sir.
Sir,
Yeah,
just 2 minutes. 2 minutes.
yeah,
Sir,
you
already
have.
I sent it to Sridhar, sir.
Yeah, PPT is there. I sent to Sridhar
I
also.
had,
I
I
can
had,
do.
I had, I had.
Yeah, yeah, you can share. It's better you can share.
Sir, it's visible now, slide?
Yeah, slide is visible. It has to be
Okay,
full
okay.
screen.
Okay.
Full screen.
Okay.
Yeah, little bit wider.
Okay, now it's visible?
Yeah, it's visible.
Okay, sir. Okay, first slide I'm moving. Yeah.
Yeah, you can. It's
You
PPT
can
or
go
PDF.
ahead.
Your yeah, it's
Now you
PPT
can.
only. PPT
Huh?
only, no? It's PPT only.
PPT only, sir.
Yeah, you can wait. First slide is over. I spoke about. If you want, I can
Okay,
speak.
okay,
Yeah,
okay. We go to second one.
yeah. I was here at this point. Yeah, that's the quantum interference where we are able to means. Yeah, you can come on to the full screen slideshow.
1 minute, sir. I will make my.
Mm-hmm. Yes. Yes, it's perfect. Yes, you can move to the
Sir,
next
you can
slide.
move, sir. You can go
Yeah,
ahead.
you can move to the next slide. Yes. Yeah, that's the quantum interference I was speaking, and it coherence and non and decoherence. This they form the part of a quantum interference, and quantum interference is very much essential as we move on to the sensitivity and unprecedented precision. We want to know about more about unprecedented precision. In that case, we need to understand quantum interference. Yeah, this is about the quantum interference. Please move to the next slide. Next slide, please. Yes, the working principles of the sensor, quantum sensor. Yeah, working. If you look at the working principle of the quantum sensor, as technology is sensor, we understand that before going into understanding the working principle of the quantum sensor, any sensor. Take about any sensor. There are two. Suppose say there are precision and sensitivity. These are the two primary. Precision and sensitivity are really important in quantum sensor as well. It is in the conventional sensor also, as well as in the case of quantum sensing as well. It's a revolutionary principles of quantum sensor based on the revolutionary sensing technology harnessing quantum mechanical phenomena to achieve unprecedented precision and sensitivity in measuring application across the scientific and industrial application. Precision and sensitivity are two important characteristics of any sensor. Precision in quantum sensing means how close your measurements are to each other, and so you are really consistent. You get a consistent reading. Similarly, sensitivity on the other hand is about how well your sensor can pick up a tiny changes in what you are measuring, so that even if something changes just a little bit, a sensitive quantum sensor will notice. For example, you can think of a smoke detector. A tiny bit of smoke detector react strongly, giving an early warnings. It should be super sensitive. Also, a super sensitive tiniest of the microphone should be able to listen to the whispers. That's called the sensitivity. And how response the sensor is response the sensor is, that is the measurement of that will be the valid point for us. Quantum sensors usually use the world wonderful properties of quantum world to make measurement. They might use, like, again, the things like superposition, where particle can be multiple state at once, or entanglement, where two particles are linked together no matter how they are apart. That's the sense quantum sensors make. They will be using the fundamental properties of superposition as well as entanglement. These quantum effects can make the sensors these quantum sensors make the sensors precise. Quantum sensing, precision and sensitivity, continuation. Quantum sensors are used in many sort of things. For example, one of the best example is the atomic clock, which is widely used in laboratories by the scientists, which are incredibly precise. What we call it as a timekeeper. So why we need these atomic clocks, that we will understand during one or two slides later, because they are not only a simple atomic clocks, it's an international standards, and these atomic clocks works in a different manner. This think of atomic clock like a super precise pendulum. Instead of switching back and forth, it uses the vibration of the atoms, which is incredibly consistent. These vibrations are so steady that they can keep the time amazing accuracy. It's a kind of like having a perfect metronome inside the clock. Similarly, they used optical lattice clocks are available. They are like a rock star of the quantum sensing world. They are so accurate that they would only lose a second every billions of a years. They might lose a second for a billions of a year. You can think of the precision, and they work on the principles of quantum computing. And here the vibration of the atoms comes into picture, and which are incredibly precise timekeepers. Again, there are squids. Squid is always a superconducting quantum interference device which can detect the tiny magnetic fields. They can even detect our own magnetic field produced by brain and art. They can be able to measure squids. They are able to detect our own magnetic field produced by the brain and the art, human brain and the art. That's how that much precise. This is that much precise they will be. Optical lattice clocks are like they lose, as I said, the billions. Imagine taking a second of splitting into the quintuple pieces. You are making a second into a number of smaller atomic level. That's how a small fraction we are talking about. It's mind-blowing precise. This precision is available only through quantum sensors. Next slide, please. That's about precision and sensitivity. And I spoke about the atomic clocks, which are a key part of the quantum sensing. They are so precise because they rely on the quantum properties of atoms, the energy levels. That's what, as and on this as and on we progress, we will be knowing about. We started with the atomic level. Now we are talking about the energy levels and transitions. This allows them to measure things like time, gravity, magnetic fields, which are incredibly accurate, where incredible accuracy, and this may find many application. Again, atomic clocks are used in a lot of things, like GPS, for example, relies on them to give an accurate location data. They are also used in telecommunication system to keep everything synchronized, and also the financial institutions where we need precise timestamps of transactions are necessary. Also in the stock markets where timestamps are exemplary needed, and GPS relies on them to give not only the accurate location, they can keep the internet running smooth and even help with super precise financial transaction. The world's most accurate atomic clock is actually a network of them called the International Atomic Time System. It's a kind of the ultimate timekeeper used to define the official time around the globe. Now we might think that how much the global clock is useful, and if the global clock are still accurate and precise and in their precision and sensitivity, then we might be still we might experience the fastest time sensing. Quantum computing could lead to breakthroughs in medicine, as all the speakers have told, designing a new drugs, understanding diseases better. We could also see advancement in material science, creating new materials with unique properties. And of course, there is a potential to revolutionize the artificial intelligence, making AI smarter and more efficient, because data is the fundamental and data processing will be faster. Definitely, there will be a smarter AI applications. Yeah, next slide, please. Yeah, and quantum sensing, beyond the classical limits, we have an atomic magnetometer. We have an atomic magnetometer. This atomic magnetometer is useful properties, useful properties. They make useful properties like atomic spins to detect the magnetic fields, and also quantum gravity meter. This measurement gravitational variations with unprecedented accuracy, and this gravimeter can we take a classical example, Mount Etna in Italy, where there is a continuous eruptions are possible, volcanic eruptions are possible. Quantum gravity meters are used by scientists to understand the frequent eruption and give the warnings as a disaster warning to the civilians. This quantum gravity meters make such a wonderful application in disaster management as well. And when you talk about optical quantum sensing, optical sensing, they employs the squeeze line and photon entanglement to exceed the standard quantum limit. We will understand in the next slide what is the standard quantum limit, and also what is that squeezed light and photon entanglement. And they are used to measure the displacement, force, and temperature in a manufacturing process. These are the fundamental: force, displacement, as well as temperature. Precise temperature in the manufacturing sector will be useful with this. Quantum sensor exploit the quantum mechanical effects to achieve precise measurement that surpass the classical sensor limitation. These devices leverage quantum phenomena such as interferometry, spin squeezing, and quantum entanglement to detect minute changes in physical quantities. What you call it as a minuscule changes in physical quantities. That's which is also a starting point for the sensor to act. Yeah, next slide, please. Yeah, what is the advantages in quantum sensing? That's what I told. If you look at the diagram, it is clear that there is a superposition of states, and there is also a squeezed state. Initially, there is a squeezed state, there is a superimposition, and there is a squeezed state. There is a superimposition state. There is a squeezed state, and the squeezed state is in order to reduce the noise. These are all the potential challenges with quantum sensing or quantum computing, how to suppress those quantum noise. And there is an entanglement states that provide a correlated measurements beyond the classical limit. That's the diagram depicts a coherent superposition states, a squeeze state, and a squeeze state that helps to reduce the quantum noise, and entangled state that provides correlated measurements. The properties like superimposition, entanglement, and quantum interference to surpass classical measurement limitation. These devices achieve sensitivity improvements of several orders of magnitude of compared to the traditional sensors. In the future slides, I'll give the numbers exact, means if not exact, but you can understand the magnitude of that differences. The quantum advantage emerges from the ability to manipulate quantum states that are extremely sensitive to external perturbations. The sensitivity combined with sophisticated quantum control techniques enable detection minute changes or minuscule changes in the physical properties. That's the advantages. There is a greater advantages in quantum sensing. Yes. Yeah, the core quantum sensing technologies, fundamentally the atomic interferometry, basically a sensor that uses atoms instead of light to measure the tiny changes in things like gravity and rotation. They analyze patterns. That is the atomic interferometry utilizes matter wave interference of that is used for acceleration, to measure the acceleration, rotation, and gravitational fields with extraordinary precision. Applications include inertial navigation system, global positioning satellites, these are the fundamental physical experiments like acceleration, rotation, gravitational fields. These are the fundamental physical experiments. Atomic interferometry, basically sensor that use atom instead of light to measure the tiny changes in these fundamental physics experiments. There is another one special type called NV centers, called as nitrogen vacancy centers, and they plays a critical role. They are used to measure the minuscule cracks or breaks in the case of diamond. NVC basically identify tiny defects in a diamond structure. You can see the picture, a diamond, minuscule changes, minuscule what you call cracks or breaks, which is unidentified by the classical methods, can be identified. Nitrogen vacancy sensors or NV centers, diamond defects serving as a quantum magnetometers capable of detecting single nuclear spins through nuclear spins, and enables nanoscale magnetic fields mapping in biological and material science application. And another one very interesting thing, strength of the electric field with incredible accuracy. That's called as trapped ion sensors, trapped ion systems. Individual ions confined by electromagnetic fields acts as a highly stable quantum centers. These highly stable quantum sensors for electric fields and frequencies and fundamental constants with unmatched accuracy is possible. Trapped ion systems used for electromagnetic fields. These are some of the fundamental core quantum sensing technologies. Yeah, the quantum coherence and decoherence, this become necessary to understand quantum coherence and decoherence, which is at a larger scale. They become a part of an interference. Imagine we are trying to measure a temperature, something really tiny. You want to we want to think that there is a super clock or a super thermometer. We might think in a classical method. However, in the quantum world, that the thermometer relies on keeping its internal quantum state stable for a long time as possible. This longer it stays stable, the more accurate the measurement. That's the what you call it as a differentiator or the difference in quantum sensors relies on maintaining coherent quantum state. That's what I initially when we talked about quantum state, there is also a coherent quantum state. That coherent quantum state for extended period, that's a long period of time, coherence time determines the sensor's sensitivity. Still, it is able to perform. Longer coherence enables better precision through extended interrogation periods, and this is only possible with respect to the property of the coherence properties, coherent quantum states. And decoherence mechanism might include that cancellation mechanism. Yes, decoherence mechanism where the cancellation is possible, and they form a larger part of a interference. And we should understand the sensing protocol architecture. What I mean to say, the sensing protocol architecture here, the architecture of a quantum sensing protocol. The protocol is a mechanism where some processing, like a communication or a data might happen. In that case, we need to have some protocol standards, and that in the quantum architecture, sensing protocol architecture is like a third party play. First, you have state preparation where you get your quantum state system ready. Then comes the state evolution, because you have seen that state transition machine. There is a transition of state from one state to another state. That's similar to that. There is a state preparation, and then there is a state evolution, and then comes the steady state. Then this is very important. The sensitivity scaling laws, or the mechanism sensitivity scaling laws, quantum sensors sensitive flows, fundamentally scaling laws that define theoretical performance limits and guide practical information. Suppose say in the first slide there was a quantum standard limit. What is that limit? Let's understand the quantum standard limit. This quantum standard limit is nothing but it's like a quantum standard limit is a classical sensor scale sensitivity with a square root of measurement time of a particle number n. It is basically the minimum amount of noise you can expect in measurement, even with a perfect equipment. That's the standard quantum limit. When you pass on to the Heisenberg limit, which is a much better, quantum sensors can achieve inverse scaling with particle number using an entangled probe states. What I mean to say that it uses the Heisenberg limit uses the quantum entanglement, which is like linking two particles together so they share the same fate. This entanglement lets us much more precision measurement than the standard quantum limit allows. The third one is the Tesla sensitivity, which is very, very important. 10 to the power of minus 19. Here, conventional NV, we came across nitrogen in centers, NV centers magnetometers, which is used in diamond precision, and it represents a minuscule changes in something that a Tesla experiment can detect. That's what 10 to the power of minus 17 you can think of the precision. And this is about, there should be some loss for sensitivity scaling loss. That's called as a sensitivity scaling loss. Root n, it is the standard quantum limit, and the inverse, that is the 1 over n, that is an Heisenberg limit. And Tesla sensitivity, it is a very, very precise, and these form the fundamental guiding principle for the sensors for an unprecedented precision, and also for greater sensitivity. The next slide, please. Yeah, we talked about the atomic clock technology and the optical lattice clocks a bit earlier, and which represents the pinnacle of quantum sensitivity precision, achieving the functional frequency stability better than 10 to the power of minus 19. These systems trap thousands of atoms in an optical lattice, and interrogating narrow atomic transition with ultra stability lasers. The world's most accurate atomic clock, it's actually a network of them. That's called the International Atomic Time System, and it's a kind of ultimate timekeeper used to define the official time around the globe. But the more than that, it finds a greater application in the keeping our internet what you call stability, and also in different telecommunication application, and also navigation, satellite GPS navigation, inertial navigation system, and GPS. And applications span as fundamentally physics test, geodesy, navigation system, and future redefinition of a second. International optical clock networks enable relativistic geodesy and search of a darker matter. Key innovation include the magnetic wavelength trapping that eliminates differential light shift. That's one of the atomic clock and optical lattice clock, how it is important and why we need sensitivity and precision. That has some significance. Next slide, please. Yeah, we have had a little discussion about the gravity meter in the earlier discussion, where quantum gravity meter and navigation. It's like having a superpower stethoscope for the Earth. Can you imagine a stethoscope for an Earth? It is highly impossible in the case of conventional technologies. That's why I told that I initially mentioned there the things which are untraceable, unimaginable, and untraceable things are possible with quantum phenomena. It's like having a super powered stethoscope for the Earth, which is unimaginable in case of conventional methods. But quantum gravimeter has that capability. Scientists are using super sensitive gravity detectors to monitor Mount Etna, which I mentioned earlier in Italy, in order to identify early risk and disaster management. And also there are laser cooling, atomic cooled to microkelvin temperature using magneto-optical traps, and polarization gradient cooling techniques are there. And as we have seen that interferometer sequence, 3-pulse sequence creates and recombines atomic wave packets with phase difference proportional to the gravitational acceleration. This is the advantages of what you call quantum gravimeter and navigation, and they are so precise. That's what they're able to. They have a good drastic. They impact significant application, not only in terms of measurement of earth magnetic fields or gravity. They also play a critical role in alerting or sending notification during the volcanic eruption. That's classical example we have discussed. The next slide, please. Yeah, industry, as we our topic is related to the industry 4.0 and how this quantum integration makes very much impactful. We are already familiar with the industry 4.0. Many applications like cyber physical system, which is an interconnected networks of physical and computational components, and that enable that enables real-time monitoring, control, optimization in manufacturing sector with seamless data exchange, and those type of data processing, high capability data processing. This quantum integration will definitely useful. And big data analytics, one of the prime area where many of the companies relies on, whether it is a banking sector, whether it is an insurance sector, whether it is a healthcare sector. Data becomes fundamental, and this data processing will becomes the big data analytics. This becomes still much faster. We can think of minutes to get, where minutes and seconds, it can be a fraction of milliseconds. It can be like that. Advanced analytical framework that processes enormous volume of operational data to extract actionable insights can be expected within a short fraction of seconds. As IoT, Internet of Things, AIoT, artificial intelligence of things, extensive sensor networks, connected devices, and collect real-time operational data. And we see that when we are working with some of the data, like some of the algorithms, we are able to able sense that we need to wait for data to process. But this might revolutionize, in quantum integration might revolutionize. Similarly, in the case of machine learning algorithms and AI system that analyzes vast data sets to predict maintenance, optimize production schedules, and quality control might enhance the quality computing. Quantum computing can help AI in a couple of big ways. First, handle they can handle way more data and calculation at once, and this means AI could learn and make decision much faster, especially in the areas like image, but and also in voice recognition. And another area we can think of, AI can be very useful as in the case of data processing area, and many other forms. It can revolutionize, and we can also say that quantum AI has a better productivity and quantum enhanced manufacturing process. And if you see the real world, let's look into the real world implementation of case studies where automotive industry, BMW Group, which came under the influence of quantum computing, and how they are benefited. They are benefited in their functional capabilities. They use quantum magnetometers and detect microscopic. They are able to detect the microscopic variation in the metal composition, ensuring consistent performance and durability. And they claim that their implementation had reduced quality control and inspection time by 40%. What improving detection rates? They are improving the detection rate in their metal composition, and automotive industries are greatly benefited. That's the BMW's case study, which shows that 40% quality control inspection time they have reduced it to 40%, and also they have improved the detection capability. Similarly, in the case of Boeing Quantum Initiative, they also took weeks to hours. Complex simulation is one of the key when particularly mission critical system and aerospace system, and which was complex simulation, which takes weeks to, and now it has reduced to hours, enabling rapid prototyping, iterative design, and improvement in and enhance their efficiency and stability. That's the another that's the another advantages which they are successful Boeing's quantum initiatives. And also, as we all know that drug discovery, landing pharmaceutical companies employ quantum sensors to molecular level analysis during the drug development, and quantum enhanced spectroscopy provide uh, unprecedented insights into the molecular interaction, accelerating the identifications of potential therapeutic compounds and reducing development timelines by 30%. All the three use cases, we come across the three case studies. In all the three case studies, they are telling that at least minimum 20 to 30% we have an advantage in the initial stages itself. When the technology goes into the rapid scale, definitely each these different sectors like aerospace sectors, not only like aerospace sectors or pharmaceutical sectors, maybe in case of data, maybe in case of banking sectors, definitely it will be benefited. These are some of the case studies where they claim that they have a very beneficial with the quantum computing initiatives. Yeah, next slide, please. Emerging application and future directions. Yeah, biomedical sensing and quantum magnetometers. We have come across the magnetometers, which enables detection of neural signals and cardiac activity and cellular processes at unprecedented spatial solution. Yeah, at a spatial solution, and NV centers, that's nitrogen centers in a diamond nanoparticles, offers biocompatible sensors for intercellular measurements. In a biomedical field, biomedical sensing, it has a greater quantum has a greater role to play. And also in the space-based system, where orbital quantum sensors enable detection, gravitational waves, and precision navigation independent of GPS satellite constellations. And distributed networks, globally connected quantum sensor networks provide correlated measurements for geophysics, fundamental physics, and early warning system for natural disasters. That's the distributed networks will also have a greater benefits. We have seen some of the success initiatives by the Boeing, also some of the success initiatives in the case of drug discovery mechanisms. And ultra sensitive quantum sensors search for axiom dark matter through resonant oscillations in atomic transition frequencies and precision measurements. That's why sensitivity and unprecedented precision, that is due to the coherent atomic states, are the driving force in case of precise measurements. Next slide, please. Yeah, technological challenges and outlook. As I said, that there are every technology has their own advantages and also the disadvantages, and challenges will be there. And how to overcome the challenges? See, when we started with the chips, we were lacking that we were lacking that we need chips in a miniature form, and later on it took years together to get its chips at a minute scale. Similarly, here also development of a chips, quantum chips sensors requires advanced microfabrication, integrated photonics, and novel material engineering materials. Silicon photonic platforms and diamond nanofabrication enable portable quantum devices, and miniaturization and integration will become a technical, will be a challenging. Also, the noise reduction. We have seen that there was noise. I see the spectrum I have shown. There was a superimposition spectrum, and there was a noise reduction, squeezing, that is a noise reduction, and then came the entanglement. You see, the earlier you saw the spectrum and noise reduction and isolation. Again, it is a challenging. Advanced vibration isolation and magnetic shielding and temperature stabilization technologies are very much essential, and implementation of active feedback systems and environmental monitoring for real-time compensation. Active feedback system is always a part of any industrial system, industrial mechanisms, and this is another challenge. And error correction and detection is always it's quite highly challenging, because developing error-free correction protocols specifically designed for quantum sensors, implementation of redundant measurement and fault tolerant mechanisms, they are a challenging part. The future of the quantum sensing lies in addressing these key technological challenges. In order to successful, these technological challenges are very much essential, need to be addressed, and quantum sensors represent a transformative technology poised to revolutionize precision measurement across scientific, industrial, and consumer application, ushering in a new era of quantum enhancing capabilities. The next slide, please. Yeah, the challenges and solutions. There are challenges, and we need to have some challenges as well. Quantum decoherence, where the cancelling mechanism we have seen during, just suppose when you throw a wave formation and wave disintegration of the wave, and challenge quantum states are extremely fragile and easily disrupted by environmental noise, leading to computational errors and reduced sensing accuracy. This quantum decoherence. There can be a solution: advanced error correction algorithms, improved qubit, improved qubit isolation techniques, and development of topological qubits that are inherently a more stable against environmental perturbation. We need to concentrate on this. And also there is a scalability limitation. Current quantum systems have a limited number of qubits and require extreme operating conditions, such as a nearly absolute zero temperature. The solution here is development of room temperature quantum technologies. Modular quantum architecture is always wise. It is always appreciable, and hybrid classical quantum computing approaches the maximum efficiency. That's what modular architecture is always in any of the classical method as well. Also in quantum methods, modular quantum architecture are highly appreciable, and development of room temperature quantum technologies becomes necessary. And there is an integration complexity, as I mentioned earlier. Incorporating quantum technologies into the existing manufacturing system requires significant infrastructure modification and specialized expertise. Same thing we face since from last 25 years, when there are already existing systems, legacy system. How to migrate this system is a greater challenge. Yeah, we can talk length about the technological advancement. We can talk length about the technological what you call, we can welcome the technology which is on the edge of the cliff, but at the time challenges are huge. These challenges need to be addressed prior to adaptation. That's what development of quantum ready middleware, standard interfaces, and comprehensive training programs for industrial implementation teams. This is integration complexity is very high. That's what the scalability as well as the integration complexity, they are to be considered in a greater preferences. Next slide, please. Yeah, the future roadmap, and let us look into the future roadmap as well as the market projection. If you look into the graph, there is a huge potential. Any technology, it is when it is used, because of the digitization, this market projection will be always super cozy, because the appreciation, it is each and every human being is adapted to the digital technology. The connecting the unconnected man has been connected. Now unconnected has been connected. That's why definitely the market projection, there is no doubt the market projection is huge, and it will continues to grow when the technology embrace and the complete embrace of the technology starts. Because the projection, if you see that there are the two graphs, one is in the black and another one is the blue. The black graph projection indicates the exponential growth in the quantum technology, technology since from 2024, from a $0 billion to $2.9 billion, around $3 in 2026, and in 2028 it is expected to reach around $5 billion. Later, it is expected by 2030, the market projection is expected to be around 8.6 billion by 2030, $8.6 billion, and maybe around $9 billion. But if you look at again, there is a graph which is in the blue color. There is also you should appreciate how much the quantum sensors occupies this space. the quantum sensors achieve the quantum sensors are equally important here. $2.9 billion in 2024. It was starting 2026. You can see there is an appreciable increase in the investment in the market value of these sensor technologies. And then in 2028 again it start increasing. Around 2030 it is expected around $3 billion. Out of $9 billion the projected market, there is an appreciable of $3 billion we need to spend on the sensor technology. The market value of the sensor technology, you can imagine that 25%, around 25% we need to invest on the sensor technology. That means to say that how much important the sensing, that is the sensitivity, the properties of the sensor, the sensitivity, that is unprecedented precision and sensitivity is needed. That's why we need to have a lot of investment on the sensors and its research. Yes, the next slide, please. Finally, the quantum industrial future, the convergence of quantum computing, quantum sensing, and industrial 4.0 represents more than a technological advancement that embodies a fundamental transformation how we conceive, design, and manufacture products. This quantum industrial revolution promised to unlock unprecedented levels of precision, efficiency, and innovation. As we advance towards the quantum-enabled future, organizers must begin preparing their infrastructure, workforce, and strategic vision. The companies that successfully integrate these technologies will not merely gain competitive advantages, they will define the next era of industrial revolution. It is not only a competitive advantage, but it is also the next era of industrial revolution. So strategically, we need to have a we need to shift this. There should be this paradigm shift. We need to embrace in a very strategic manner. Excuse me. That's all to say about few words about this. But I have also, as there is a time persists, I can show a weather system as an example and how quantum thinks. If I am able to share the screen, if I given, I need Sridhar, Dr. Sridhar, I need sharing permission, so that this time I will be, because they are a PDF word and it will be easily shareable. I don't.
Shall I play this video?
Yes, if you have a video, you can play it.
On-
If you have a video, you can play it from. If you have all the documents, you can play it. No problem. It's a very interesting 1 minute video, which will mind blowing video. Yes.
Quantum computers are already outperforming the world's most powerful.
1 minute, sir.
Yeah.
Supercomputers, thanks to the
It's
power of
visible?
quantum physics.
Yeah, it's visible.
Our world-leading performance is based on the quantum charge-coupled device architecture. It all starts with the qubit, or quantum bit. We use nature's qubit, a single charged atom known as an ion. By using electromagnetic fields, ions around and trap them above the chip in our vacuum chamber. Our ability to move ions around means that we can bring any two ions together, which gives us all-to-all connectivity. All-to-all connectivity massively increases our computing power and allows for maximum flexibility in error correction and algorithmic design. We control our qubits with lasers, giving us unparalleled precision. We use lasers to initialize, gate, entangle, and measure our qubits. Thanks to our all-to-all connectivity, we can gate and entangle any two qubits. All computations are composed of these basic operations. Measurement works by checking if the qubit absorbs or doesn't absorb the photons in the laser light. Many computers can only perform measurement at the end of the computation because it will collapse the qubits into a classical state. Our computers have a unique ability to perform measurements anytime during the circuit and to reuse the measured qubits. As our systems continue scaling, our computational power grows exponentially. The addition of any single qubit to the system doubles the information we can compute with. A new era of computing starts now. What could you do with the world's highest performing quantum computers?
So it's finished.
Yeah, one more is there. One more 2 minutes. One more 1 minute video is there. Microsoft and Quantium demonstrate the more reliable logical. This one, the next one is there. I shared to you. I
one
shared to
minute.
you. Yeah, I
You
shared
shared
to
with
you.
me?
Yeah, I
Okay.
shared it to you.
Just now you shared?
Yes, just now I shared. Yes.
Okay, 1 minute. Sir, file is not in the format, playable
Yeah,
format.
yeah, it's okay. No problem. No problem. You can share this one. The tools which are used for the quantum machine learning. That these are the complete WML section is there. You can share this PDF. You can share the PDF. Just now
Okay.
PDF. Yeah.
PDF I will share, sir.
Yeah, PDF you can share it. It's a very informative and the implementation part of the aspect. Yeah, just now you can.
1
Yeah.
minute, I will open.
Yeah. Or you permit it will open. PDF will open. There is no problem at all from my side.
Opening PDF. It's
Yeah.
visible?
Yeah. Just a moment.
Sir, it's visible? Sir? Hello?
Sir, visible,
Yes,
sir.
sir.
Sridhar sir, it's visible.
Okay, sir, okay. Sir, all this PDF file we will share with the participants. Okay. Sir, Chetan sir, it's Rakesh sir is muted. So can you unmute him?
Okay, sir, inform, sir.
Okay. Rakesh sir, now? Rakesh sir?
Yeah, now it's yes.
No, yes, sir, you know.
Yes, now you are permitted. You are permitted.
Yes, sir, you can go
Yeah,
ahead, sir.
yeah, just now the host has been permitted. I was unmuted and the host has permitted now. And you can see that the tools and techniques, which are very much essential. QSkit is a really powerful tool from IBM, and that lets you to work with quantum computers. It's like a setting of building blocks that you can use to create and run the quantum programs. And from the you can go to the next move a bit and yeah, there is a and even collab Google Colab is there. Through that we can run this we can import the use a kit, use a fundamental things, and also there is a penny lane which forms a very very wonderful platform where you can have a simulations and there is also what you call this penny lane. Each has its QSkit has its own advantages, and penny lane has more advantages in terms of QML, and it's very precise, and it's very you can really have a benefit of this. Next slide, please. And we have developed. Yeah, next you can move the slide. You can move the slide. You can do the next one. Yes, yeah, next. You can move the next. You can move to the next level. Yeah, next or else next. Yeah, yeah, that's what. Yeah, these are the things. Yeah, and that's what there is a quantum circuit, and we need to build a circuit which is with the circuit can be built through the qset library, qset platform, and also the quantum register. We are able to define and create a register using quantum register can be built, create a register with the 2 qubits, and also the quantum circuit where you can create a circuit, and then it's possible to create an environment, simulated environment, because as long as we don't have a real hardware, we can simulate this, and we can show how this performance is possible. You want me to, if you Sridhar, can you allow me the screen sharing? I can show the last through example. I can show it.
Sir, okay, sir. Sir,
Yeah.
can sir is poster. Will you
Yeah.
allow him to share?
Yeah, Chetan, if you allow me, then it's possible to share one small last demonstration with respect to QSkit as well as the
Okay, sir. Sir, I will stop my
yeah,
screen.
yeah,
Okay, now you can check, sir, whether it is allowed.
yeah. I'll check. Yeah, I'll check a minute. It takes a minute. If I'm able to share, then I can show the one simple, very good example. Good example of yeah. One minute. 1 minute. I'm sharing the example of a weather station through example. It takes bit time in Google Colab. Is the screen shareable?
No, sir, it's not visible.
It's not visible. But just last try. I can give a last try. Otherwise, we'll try to wind off. Yeah, just a moment.
Sir, you check it out, sir. It's not visible.
Okay.
Yeah,
If not visible, yeah,
no, not visible.
not visible. Yeah,
No.
just a moment. It's not visible. You can close it.
No, it's visible. You just, yeah.
I think it's visible. Something else.
Yes, sir, screen. You go to that Google Colab, sir. That tab. Yeah.
It's coming. Google Colab is coming.
Yes, sir, it's coming. Yeah.
It's visible. Oh.
Visible.
Yeah, then if it's visible, I can give you more information about this. Yes, this is the Google Colab where you are able to, there is a, what you call it as a import NumPy, as we are very familiar with. Are you able to see from QSkit import quantum circuit? Is it visible?
Yes, sir, visible. Go
Is
ahead.
it visible? Yes, then more things can be spoken about that. Quantum circuit is a blueprint for your quantum program, and it's where you define the qubits you will use, and the operations of qubits. Qubits are the basic units, as we know, and that we need to import it. And there is, again, you can see that there is we are from the QSkit. We are able to QSkit. We are able to set up an environment here, get a random numbers. The code uses a NumPy for generating a random numbers, and also handling the arrays, which simulates environmental sensor data like temperature, humidity, and air quality. The time library is used. The time library is used here. Time library, we use a time library to introduce process between simulation runs, and also and also making the outputs easier. The JSON module here, you can see the JSON module, and this JSON module formats the predictions neatly from printing. That's the output. And from QSIT, several components are used. There is a quantum circuit, builds custom quantum circuits, and while Z feature map, there is a Z piece. You can see the Z feature map, and what the Z feature map as well as the real amplitudes provide a pre-built quantum circuit for feature encoding and variational, and as useful in quantum machine learning models. The Cobay law, which is there, and that is that the optimizer for QSIT algorithms, QSIT algorithms optimizer is used to optimize parameters of variational circuit during training. The variational quantum classifier from the QSIT machine learning provides a framework for building and training hybrid quantum classical classifiers. The AER simulator. This is a simulator, AER simulator, and served as a backend to simulate the quantum, and it is available here. You can see here AER simulator. We are using that AER simulator. QSET underscore AER from the package of QSQuit serves as a backend to simulate quantum circuits without requiring actual quantum hardware, and that's the advantage of a or backend simulator. And the quantum weather station, we have created a weather station and weather station class that encapsulates everything. It collects simulated sensor data, normalizes it, and builds upon quantum models in a collect sensor data. Random environment values are generated. Random values, we have taken the random packages are there, and encode. You can see the weather, predict weather conditions, self sensor data, quantum circuit prediction. You have an encode data. The predict weather condition methods builds upon a custom circuit. The custom circuit, and that encodes sensor data into qubits using a rotational gates, and introduce entanglement with CNOT gates. Here CNOT gates, you can see the CNOT gates, where you can see the CNOT gates. This is the implementation aspects, where you can see encoded data, more likely measurement, and finally into this iteration we have come across. Before that, there is a CNOT gate, and that gate is useful. CNOT gate, and then measures results, the interpretation quantum results, and we are given it 3 iterations we are given, and we see all the things, quantum entanglement, and what we've spoken about, all the things till now we can able to run in simulation, and we are able to. I given 3 iteration, and I run this model. Iteration 1, sensor data, normalized sensor data, and their temperature trend stable, humidity level is normal, and air quality status is good. What we have considered here. Second iteration, you can see the second iteration again. There is a result, and also in the third iteration, sensor data, normalized sensor data, we are able to make it. That's how we need a QML, or a quantum machine learning language, QML language, to run the quantum sensor in order to understand the practical way of implementing. And we are deeply committed at ATAL level software. We have some simulations, particularly we have set up a weather station using the simulation software. And when we get an hardware, we are eagerly waiting for that, and deployment to the hardware. But still, it's a long way to go, and there is a lot of research need to be done, and facilities we are seeking. And pennyline.ai is one such opportunity where we are able to get some. We are talking to the company where we can get an hardware, their interface hardware, where we can some of the features can be done. And that's the opportunity. It's a great opportunity, making me to express some of the views from our perspective. And thanks to our wonderful audience. Thank you very much. There was some interruption. I don't know. It is very simple. I would always share this. It's a quite simpler. Just share the slide and immediately get it to the full screen, FIR full screen. But unfortunately today I didn't come. I didn't make it. But still, I gave my friend Dr. Sridhar Payne to entire what you call session to navigate the slides. I am really sorry for that. I'll just recover these things in the next session future. Thank you very much. Thanks for an opportunity. Wonderful audience. Thank you very much.
We have around 10 more minutes to wind up this session. If anyone has any questions or clarification, please feel free to ask.
Yeah, you can, because Madam told that 7:30 there is a session, so that you complete it around 10:20, 7:20.
5 more minutes, sir.
Yeah,
If
yeah, no
anyone has
problem.
any questions,
No, I don't have any.
clarification, please.
I don't have any objection. Yeah, that's what. Yeah, that's the reason. Yeah. Yeah, that's what. Yeah, this is Quisit and Pennyline. These are the fantastic tools for quantum computing, but they are slightly
Devraj
different.
sir, please enable the unmute option for all the participants so they can ask their questions directly. Devraj sir,
Sir,
please enable the unmute option for all the participants so they can ask their questions directly. So it will be more effective.
Uttam sir, it could be better. I think they can raise the hand. Okay, so it could be better. Okay, if everyone, if it is they ask the questions, it's difficult to answer it. It could be better if they're having any doubts or any clarification they need. If they raise the hand or if they put in the chat box, it could be better. I think. Yeah,
Okay, sir.
Yeah, that will be a better idea.
yeah, yeah.
If you can
Participant,
raise
please
the
type
hand
them in the chat
or
box if any
yeah,
questions is there. Only
yeah.
5 more minutes is there.
Yeah, you can raise the hand or you can put it in the chat box or you can, I have given my ID also. It can be offline also. Anything is fine. Anything is fine for me.
So better you type them in the chat box. Only
Yes.
5 minutes there.
Yeah.
Hello.
Yeah.
Hello, sir.
Yes.
Sir, what you mentioned about quantum gravimetry?
Yeah, okay.
Okay, what exactly the principle behind that, sir?
Gravimetry, principle behind gravimetry.
Yeah, and what is the use of that?
Yeah, I know the means the functionality perspective, the gravimetry that is useful in order to measure the gravitational impacts, the gravity of the this one Earth gravitational force. Based on that, the application wise, they are utilized in the disaster management. That the example I gave you. As a part of the Mount Etna in Italy, they were able to use this in order to measure the Earth's based on the they use the what you call it as an the spins, the rotation, the revolution, the spins, as well as the some of the parameters related to the Earth gravitational force. In that way, they might use that in that sense. Yes.
Dear participants, audio button is enabled. If you have any queries, kindly ask.
Okay, sir. So thank you so much for your insightful and engaging session. Your valuable knowledge and perspective have truly enriched today's program, sir. We are grateful for the time and effort you have taken to share your expertise with us. Thank you once again, sir. Like I said, thank you so much.
Yeah, I have mentioned in the chat regarding the sir's answer, the fundamental principle behind quantum gravimeter, which involves, I also mentioned that in earlier, there was a cloud of ultra cloud atoms, which was mentioned in one of the slides. And just I came to that slide and often cesium of test masses to sense the gravity. The process unfolds laser coding, cooling, that also I mentioned in one slide. And as you know, superposition, these are the things it is mentioned there, and that is the fundamental principle which in my understanding it is used in a gravimeter, atomic interferometry and gravitational acceleration by leveraging the principles of quantum mechanics. Thank you very much.
Thank you so much, sir.
Yeah, thank you.
So, dear participant, now we move on to the next session. It's my privilege to welcome our one more esteemed resource person, Mr. Raghuraj D, who will be enlightening us on uses of quantum sensor in smart manufacturing. His expertise and experience in his domain will surely add a great value to our learning. Now it's time to introduce our extreme resource person, Mr. Raghuraj D, software engineer, Accenture Solution Private Limited. Mr. Raghuraj D completed his BE in Computer Science and Engineering from Sridevi Institute of Engineering and Technology. He began his career at ISRO, followed by the role of MMP software as a trainer engineer. After 10 months, he joined Accenture Solution Private Limited, where he has grown into the role of team lead. His current client is Bank of America, and he has contributed to the development of enhancement of multiple applications. Over the year, he has received a several recognition at Accenture, including the Spot Award, ACE Award, and Innovation Award. In addition to his professional responsibility, he actually contribute to the organization team event. Behind his corporate achievement, Mr. Raghuraj has a strong background in extracurriculum. During his college days, he was an active member of the NCC and earned Rifle Shoot certificate. With his blend of technical expert, leadership skill, and extracurriculum achievement, Mr. Raghuraj D continued to inspire and lead by example. And one more thing, he is my alumni and we are feel proud to have him here with us today. So with great pleasure, I now invite Master Raghuraj to begin the today's session.
Thank you so much, Susan sir. Hey, hi all. Good evening. So today I'm going to talk about quantum technologies in the industry. So let me share my screen. Is it audible?
Yeah, it's audible. Raghuraj,
Yeah.
share your screen.
Yeah, sure.
Ah.
Is it visible now?
Sir, visible, you just, yeah, sir. You just go to
Now it's
your
visible.
yeah,
Maximize the screen.
Yeah.
slideshow. Yeah, yeah. It's visible.
Yeah, now it's nice.
Yeah. So today I'm going to give a brief about use of quantum sensors in smart manufacturing, how it involves in manufacturing and other details. So this is the comprehensive session overview of understanding quantum sensing fundamentals in quantum mechanics principles, how we are integrating this quantum in industry 4.0, how we are analyzing quantum sensor in applications in industrial environments, and examining real world case studies and implemented strategies, discussing future trends and market opportunities in the industries. So these are the detailed topics to deep dive. So I will go one by one, like quantum sensing technology introduction and how we are implementing this quantum in smart manufacturing and industry 4.0, the types of quantum sensors and operating principles, how we are applications in manufacturing quality control, predictive maintenance using quantum sensors, and also how we are using this quantum in materials testing and defect detection. So, and also integration with IoT and smart factory systems and real world case studies and success stories. So, what are the challenges and implemented strategies, market trends and future opportunities, and technology roadmap and implementation plan? So, let's go to the introduction. So, quantum sensing is a rapidly advancing field that uses the principles of quantum mechanics, such as superposition, entanglement, and quantum coherence to measure physical quantities with unprecedented precision. Unlike classical sensors, quantum sensors exploit the unique behavior of quantum systems, atoms, photons, ions, or superconducting circuits to detect extremely small changes in fields, time, or energy. So, key principles in quantum is superposition, is nothing but a quantum system can exist in multiple states simultaneously, enabling highly sensitive measurements. Entanglement is nothing but correlated particles improve accuracy and noise resistance. So, quantum coherence maintains stable quantum states that can be used as precise reference standards. So, types of quantum sensors: atomic clocks, ultra precise timekeeping, quantum magnetometers detect minute magnet fields used in brain imaging and navigation, quantum gravimeters measures gravitational acceleration with high accuracy. So that is useful for geology, oil, and mineral exploration. So quantum sensing was as classical sensing is nothing but a sensitivity that is 1000x more sensitive than classical counterparts. A stability is a built-in calibration through quantum mechanical constants. A resolution, nanometer scale, spatial resolution capabilities, operating conditions. It may operate at room temperature. So core advantages for industrial applications is self-calibrating sensors based on physical constants, continuous monitoring without significant trade-offs, and detection of extremely subtle environmental changes. So main applications involves healthcare, that is brain imaging, MRI enhancements, defense and navigation, submarine navigation without GPS, earth science, mineral exploration, groundwater detection, space exploration, mapping gravitational fields of planets, telecommunications, that is used in time synchronization in networks. So the advantages of quantum is extreme sensitivity and accuracy, ability to detect signals invisible to classical sensors, reduction in reliance on external references like GPS. And the challenges we have in quantum is like maintaining quantum coherence. Systems are sensitive to noise and environment, high cost and complexity, scaling from lab research to commercial devices. So let's go to the smart manufacturing and industry 4.0 fundamentals. So introduction is industry 4.0, the fourth industrial revolution, represents the integration of digital technologies into manufacturing, creating smart factories. A manufacturing uses data, connectivity, and automation to enhance efficiency, flexibility, and productivity. Evolution of industry, that is industry 1.0, industry 2.0, industry 3.0, and industry 4.0. See, industry 4.0 is cyber physical systems, IoT, AI, big data, cloud computing, and smart manufacturing. Whereas industry 3.0 is nothing but automation with electronics, IT, robotics. Industry 2.0, mass production, assembly lines, and electricity. Industry 1.0, mechanization, that is steam engines, water power. This is the evolution of industry. So core pillars of industry 4.0, that is internet of things, connected machines, devices, and sensor sharing real-time data. Cyber physical system, that is CPS, integration of physical machinery with digital control. Big data and analytics, that is transforming raw data into actionable insights. So cloud and edge computing, that is storing, processing and accessing manufacturing data globally. Artificial intelligence and machine learning is predictive maintenance, demand forecasting, quality control. Robotics and automation, that is collaborative robots, autonomous systems. Augmented reality, that is AR and VR, virtual reality. So it's in training, maintenance, and remote support. And finally, we have cyber security, that is protecting connected systems from threats. So smart manufacturing fundamentals, interoperability, that is machines, devices, and people communicate seamlessly. Real-time capability, that is instant data collection and decision making. Decentralization, that is systems make decisions autonomously without central control. Virtualization, that is digital twins simulate and optimize processes. Modularity, flexible adaptation to changes in demand or product type. So benefits of industry 4.0 is improved productivity and efficiency, reduced downtime through predictive maintenance, enhanced product quality, greater flexibility in production, cost saving through optimized resource utilization, better decision making via real time data. So same similar to quantum, we have some challenges in here also in 4.0, that is high initial investment costs, data security and privacy concerns, integration with legacy systems, workforce skill gaps, that is need for digital literacy, standardization issues across industries, and also applications is automotive, that is autonomous production lines, electronics, precision manufacturing, pharmaceuticals, smart labs and quality tracking, energy and utilities, smart grids and predictive maintenance, supply chain, real-time tracking and smart logistics. So the roles of sensors in smart manufacturing is the foundation of data collection for all smart manufacturing process, enable real-time monitoring and control of production systems, provide critical inputs for AI and machine learning algorithms, support predictive maintenance and quality assurance programs. So current sensing limitations is limited sensitivity for detecting micro defects at early failure signs, calibration drift requiring frequent maintenance and recalibration, inability to measure quantum level phenomena in materials, restricted operational environments due to temperature and electromagnetic requirements. So next we will move on to the quantum sensors and what are the technologies and principles involved in quantum sensors. So types of quantum sensors, technologies and principles: automatic atomic clocks, that is quantum time sensors. Principle, what is the principle for atomic clocks is based on the quantum transitions of atoms, example cesium, rubidium and strontium. Atoms oscillate at highly stable frequencies. Counting these oscillations defines time with extreme precision. And technology wise, cesium atomic clocks used in GPS, optical lattice clocks, ultra precise, next gen time standards, applications like GPS, telecom in synchronization, financial systems. Quantum magnetometers principle, measure tiny magnetic fields using in spin states of atoms or quantum defects, changes in magnetic field shift, energy levels of atom ions which can be detected optically or electronically. Technology wise, optically pumped magnetometers, that is called OPM, NV, that is nitrogen vacancy, centers in diamond, use electron spin resonance. Applications: brain imaging, that is MEG, zoology, detecting submarines, and mineral exploration. And third one is quantum gravimeters, that is are nothing but gravity sensors. And principle is use atom interferometry, that is atoms cooled to near absolute zero act as matter waves. When subjected to gravity, their interference pattern shifts, allowing ultra sensitive gravity measurements. Technology: cold atom interferometers, portable quantum gravimeters. Applications: oil mineral exploration, underground tunnel detection, earthquake prediction, and geophysics. Just give me a minute. So, quantum sensors in manufacturing control. I see chemical process control, that is molecular level chemical sensing, detection of trace chemical contamination, monitoring of chemical reaction progress, quality control in pharmaceutical manufacturing. So benefits for manufacturing quality is zero defect manufacturing through early detection, reduced waste and rework costs, enhanced product reliability and consistency, compliance with stringent quality standards, and real-time process optimization capabilities. So predictive maintenance using quantum sensors. So transforming maintenance through quantum sensing is early failure detection. So magnetic field analysis for equipment health, detection of bearing wear through magnetic field changes, monitoring of electric motor magnetic signatures, early identification of mechanical misalignments. So in quantum sensor for electromagnetic fields, that is principle is atoms or ions act as ultra sensitive probes to detect electric fields. Shifts in atomic energy levels reveals the presence of electromagnetic radiation. And technology wise, Rydberg atom sensors highly excited atom sensitive to microwaves and RF fields. So application wise, we can consider 5G, 6G communication testing, RF detection and security. And also we have last one is quantum thermometers. The principle used in quantum thermometers is atomic ionic transitions or spin states to detect tiny temperature variations. Technology used in quantum thermometers is NV centers in diamond, that is temperature dependent spin properties. Applications wise, medical diagnostics, nanoscale material science, and quantum computing stability. So we'll move to the next slide. So material testing and defect detection applications. Materials testing and defect. One second. So quantum sensors in materials testing and defect detection, it's nothing but a traditional non-destructive testing, that is NDT methods. X-ray, ultrasound, eddy current are effective but have limits in resolution, sensitivity, and material penetration. So quantum sensors surpass these limits, enabling high precision, non-invasive detection of micro defects, stress, and hidden structural issues. So quantum sensor technologies in material testing is quantum magnetometers, applications, principles, and so on. So this is non-destructive testing, NDT revolution, subsurface defect detection, that is quantum magnetometry for detecting hidden cracks and voids, imaging of internal structure without damaging materials, detection of delamination in composite materials, evolution of weld quality and integrity. Ferromagnetic material analysis is a detection of material fatigue before visible cracks appear, monitoring of heat treatment effectiveness, assessment of material hardness and properties, and advanced composite materials testing, that is carbon fiber composites, that is detection of fiber breakage and matrix cracking, monitoring of manufacturing and assessment of impact damage in the environment. So in the aerospace materials, critical component inspection for aircraft safety and detection of stress corrosion cracking, evolution of additive manufactured parts. In the semiconductor and electronics testing, wafer level defect detection, a mapping of dopant concentrations, a detection of crystal defects and dislocations. In the semiconductor and electronics, evolution of thin film properties. And package level testing, wire bond integrity assessment, detection of die attach defects, thermal interface material methods, a room temperature. And the key advantages in materials testing is detection sensitivity is 1000x better than conventional methods, and room temperature operation eliminating complex cooling systems, non-contact and non-destructive measurement capabilities, simultaneous multi-parameter measurements, and also it's high spatial resolution for detailed defect characterization. So integration with IoT and smart factory systems. So how we are implementing this quantum sensors in industrial IoT architecture, that is IoT network integration, sensor to cloud connectivity, quantum sensors as edge devices in IoT networks, real-time data streaming to cloud platforms, integration with existing SCADA and MES systems, wireless and wired communications support, and data quality enhancement, ultra high precision data improving AI ML model accuracy, reduced sensor noise leading to better analytics, self calibrating sensors eliminating drift errors, and smart factory integration architecture, edge computing implementation, local processing of quantum sensor data, real time decision making the edge, reduced latency for critical control applications. So, digital twin integration is nothing but quantum sensor data feeding digital twin models, high fidelity virtual representations of physical assets, predictive modeling with unprecedented accuracy. So, advanced analytics and AI integration, that is machine learning enhancement, high quality sensor data improving ML model training, detection of subtle patterns invisible to classical sensors, predictive analytics with extended time horizons, anomaly detection systems, so ultra sensitive detection of process deviations, early warning systems for quality control, automated response systems for process optimization. Implementation considerations, network bandwidth requirements for high resolution data, data security and encryption for sensitive measurements, standardization of quantum sensor communications protocols, integration with existing enterprise systems. So let's move to the real world case studies and success stories. So industry success stories and implementations in automotive and manufacturing, BMW case study. So application is quantum sensors in quality control systems, and implementation was is a NV center magnetometers for detecting microscopic defects, and results is 40% reduction in warranty claims related to manufacturing defects, a 25% improvement in first pass yield rates, early detection of component failures, saving $2 million annually. So aerospace industry, Boeing implementation. So application is composite materials testing using quantum magnetometry. Implementation, a detection of delamination in carbon fiber components. So the results is 99.9% defect detection rate versus 85% with traditional methods. So 30% reduction in inspection time, enhanced safety compliance and regulatory approval. So in semiconductor manufacturing, Intel quantum sensors, so application is wafer level defect detection and characterization, quantum magnetometers for dopant mapping. The results is 10x improvement in detection sensitivity, 50% increase in chip yield through early defect identification, reduced time to market for new semiconductor processes. So in energy sector also, Siemens wind turbine monitoring. So application is predictive maintenance of wind turbine components, and the implementation is quantum vibration sensors for bearing monitoring. So 50% result reduction in unplanned maintenance events, a 20% increase in turbine availability, and 1.5 million annual savings per wind farm. So in the pharmaceutical manufacturing, quantum chemical sensing, application wise, real-time monitoring of chemical synthesis process, and the implementation is quantum sensor for molecular detection, and the results is 99.9% purity achievement in drug manufacturing, 30% reduction in batch reduction rates, and also improved regulatory compliance and faster approvals. So on challenges and implementation strategies. So implementation challenges and mitigation strategies is as follows. Technical challenges, environmental sensitivity. The challenge is quantum sensors sensitive to electromagnetic interference. Solution is electromagnetic shielding and isolation techniques. Best practice is to controlled environment design and monitoring. Integration complexity. So challenge complex integration with existing manufacturing system. Solution is phased implementation with pilot programs. Economic challenges, high initial investment, so it requires a highly quantum sensors cost is 100x more than classical sensors. So we have to focus on high value applications with clear ROI. Start with critical process and scale gradually. So environmental sensitivity is nothing but quantum sensors are affected by temperature, vibration, and electromagnetic noise. So maintaining quantum coherence, difficult to sustain stable quantum states outside controlled labs. Miniaturization, that is, many prototypes are bulky and not at production line friendly. Integration with legacy systems are to fit into existing manufacturing lines and Industry 4.0 frameworks. And economic challenges like high cost equipment and maintenance, limited large scale production, that is, many sensors are still at prototype or pilot stage, uncertain ROI, that is, return on investment. Companies hesitate to invest without proven industrial benefits. So workforce challenges like skill gaps requires expertise in quantum physics, engineering, and data analytics. Training needs. Operators and engineers need upskilling to handle advanced quantum tools. Standardization and certification. Lack of global standards for industrial quantum sensing. Regulatory approvals for use in critical sectors like aerospace and defense take time. And implementation strategies, pilot testing and use case focus. We can start with specific high value applications, example crack detection in aerospace turbines, semiconductor defect inspection. Run pilot projects to prove feasibility before full scale rollout. Hybrid approach. So in the hybrid approach, we have to combine quantum sensors with conventional NDT methods for cross validation. Use quantum only where classical methods fail, nano defects, hidden voids. Collaboration and ecosystem development. So, partner with universities, research labs, and startups for co-development. Join industry consortia, that is example quantum technology hubs, to share cost and expertise. Cost reduction and scalability. Focus on mini and chip-based quantum devices. Develop portable, robust quantum sensors suitable for factory environments. Workforce development. Train engineers in quantum technology plus Industry 4.0 skills, that is AI, IoT, data analytics. Create cross-disciplinary teams, physicists plus manufacturing experts. Integration with digital manufacturing. Link quantum sensors with IoT platforms and digital twins for real-time process and optimization. Use AI and machine learning to interpret quantum sensor data and automate QC decisions, that is quality check decisions. So roadmap for industrial adoption. Research and development, lab-based prototypes, feasibility studies, pilot implementation, small scale industry trials, standardization, that is develop certification frameworks for NDT and QC, commercial scaling, cost reduction, portable devices, integration with Industry 4.0, and also is a mass adoption. So in overall, quantum sensors face challenges in stability, cost, and integration, but with pilot-driven adoption, hybrid QC strategies, workforce training, and Industry 4.0 integration, industries can gradually transition towards scalable, real-world quantum sensing applications. So market trends and future opportunities. So quantum sensing market analysis and growth projections is as follows. So current market trends, a growing investments, that is governments, US, EU, China and India funding quantum technology programs, raising venture capital in quantum startups, that is quantum sensors for defense, medical, navigation, defense and aerospace dominance, primer early adapters, that is GPS independent navigation, submarine detection, and aircraft safety, demand for gravitational and magnetic anomaly detection, shift from lab to industry. So prototypes moving towards field deployable, portable, and robust devices. Focus on miniaturization, that is for commercial and consumer use. In industry, integration with Industry 4.0, healthcare applications emerging, that is quantum magnetometers for non-invasive brain and art imaging, and also quantum MRI and biosensing are gaining traction. So and also future opportunities is like manufacturing and quality control, ultra precise defect detection in semiconductor, aerospace, and automotive, ensuring reliability in 3D printed parts, inline quantum sensor for smart factory monitoring, and also in the navigation and transportation, quantum gyroscopes and accelerometers for GPS free navigation, aircraft, spacecraft, and submarine guidance systems, and also in the energy and natural resources, detecting underground oil, gas, and minerals using quantum gravimeters, pipeline and structural monitoring to prevent leaks or failures. Also, healthcare and life sciences, early diseases detection via quantum enhanced imaging, nanoscale thermometry for drug delivery research, quantum biosensors for point of care diagnostics, telecom and cyber security. In the field of telecom and cyber security, synchronization of 5G, 6G networks using quantum clocks is very much useful in the telecom industry. And also in the field of cyber security, Rydberg atom sensors for electromagnetic signal detection, space exploration, so quantum gravimeters and magnetometers to study planetary fields, navigation for deep space missions without reliance on earth-based signals. So if you consider market growth outlook, so current market is 2025, so 700 million to 1 billion globally, and projected markets in the 2030 is 1.5 billion to 3.0 billion, with a CAGR of 15 to 20%. So long-term projection around 2040 is 5 billion to 10 billion market potential. So in the industry 4.0 adoption, quality requirements and cost reduction. So regional leaders in this one is US, Europe, R&D and D and aerospace, China, that is large scale defense adoption. India and Japan comes under telecom, space and healthcare use cases. So key drivers, demand for precision and reliability in critical sectors, push for GPS independent navigation, growing industry 4.0 adoption, that is smart factories. So barriers to adoption is like high upfront cost. So environmental sensitivity is one other factor, lack of industrial standards and certification, and also shortage of skilled quantum workforce. In overall, so quantum sensing is transitioning from defense-driven prototypes to commercial, healthcare, and manufacturing applications. The next decade will see a miniaturized, scalable, and AI integrated quantum sensors that is powering smart factories, healthcare, telecom, and navigation systems with a projected multi-billion dollar market by 2035. It's a projected. So we'll go to. So next topic is ROI and business impact analysis, that is return to investments and business case analysis. So initial capex, that is capital expenditure, acquisition cost of quantum sensors. This is currently high due to limited production, and also setup and integration with existing industry 4.0 systems. OPEX, that is operational expenditure, maintenance and calibration costs, skilled workforce training, cyber security and data management is also one of the aspect. And in respect to ROI drivers, where that is value creation, as a direct benefits like reduced defects and scrap, early detection of micro cracks, porosity and stress, that is less material wastage. Example, aerospace turbine blade defect reduction could save millions per year. Downtime reduction, so quantum sensors enable predictive maintenance, preventing a single unplanned stoppage in automotive or semiconductor fabs can save 1 million in lost output. So productivity gains, inline quality monitoring, fewer revokes and delays, shorter inspection times versus traditional NDT, and also indirect benefits, regulatory compliance meets stricter safety quality standards, brand reputation, so higher customer trust through improved reliability, market differentiation, that is early adapters can command premium pricing. If you see ROI calculation framework is Cost savings, reduce scrap rate, lower downtime, revenue gains, and also business impact by sector wise. So manufacturing, that is automotive and aerospace, is one of the leading in the manufacturing. Lower defect rates, higher safety and fewer recalls. So return to investment in this sector is high. A short payback, 1 to 2 years. Semiconductors and electronics detects nano defects in wafers, chips, reduces costly rejects, and return to investment very high, saves millions per fab cycle. Energy and oil gas pipeline monitoring and defect detection prevents catastrophic failures. Return to investment is medium to high. It depends on failure prevention cost avoidance. And in healthcare, pharma, quantum enhanced imaging, drug consistency testing, it's a long term, though. So return to investment is long term, but strategic impact on innovation. Defects and space, navigation and surveillance applications, non-financial strategic value, implementation strategy for maximizing ROI. So this is a technology roadmap and implementation plan. So near-term developments, that is 2025 to 2027. So technology maturation, improved room temperature quantum sensors, enhanced sensitivity and stability, reduced electromagnetic interference and susceptibility, standardized interfaces and communication protocols, manufacturing integration is a plug and play quantum sensor systems, pre-configured solutions for common applications, integration with major IoT platforms, and simplified installation and commissioning. So, in the medium term advances 2027 to 2030, it's a technology scaling. So, mass production and reducing sensors cost by 70 to 80%, miniaturizations enabling broader deployment. So, multi parameter sensing in single devices. Also, AI powered sensor fusion and analytics. In the application expansion, deployment across all manufacturing sectors, integration with autonomous manufacturing systems, a real-time process control and optimization, supply chain visibility and traceability. It's a long-term vision, that is 2030 plus. Quantum sensors as standard manufacturing components. So it will become a standard manufacturing component, self-organizing sensor networks, and quantum enhanced digital manufacturing ecosystems, fully autonomous quality control systems. So implementation roadmap for organizations is in the first year, pilot projects and proof of concept. In the second year, limited production deployment, and then the third year, scaling and optimization. In the fourth year, full enterprise integration and innovation. So, in the conclusion and strategic next steps, so this is the key takeaways and strategic insights. So, summary of key points: a quantum sensor represents a paradigm shift in manufacturing precision. Applications span quality control, predictive maintenance, and materials testing. Integration with IoT and smart factory systems creates powerful synergies. Early adopters are already seeing significant ROI and competitive advantages. Market growth projections indicate massive opportunity over next decade. Critical success factors, that is strategic selection of high impact applications for initial deployment, strong partnerships with quantum sensor technology providers, investment in workforce training and capability development, phased implementation approach with clear milestone tracking, integration planning with existing manufacturing systems. So immediate action items, it is for manufacturing leaders. identify pilot applications with IES return to invest potential, establish partnerships with quantum sensor vendors, develop business cases for quantum sensor investment, plan workforce training and capability building programs. So for technology teams, assess current manufacturing systems for integration readiness, design quantum sensor integration architecture, develop data analytics capabilities for quantum sensor data, and to create testing and validation protocols. Future opportunities is like quantum enhanced autonomous manufacturing, real-time supply chain optimization, predictive quality control systems, and sustainable manufacturing monitoring. So, in summary, quantum sensors I bring I return to investment by reducing scrap, downtime, and defects while enabling compliance and innovation. Early adopters in aerospace, semiconductors, and automotive. So, automotive see the fastest financial returns while others benefit more strategically. So extended view. So in the ROI and business impact of quantum sensors in the detailed ROI dimensions. So there is one more, that is operational return, financial ROI and strategic ROI. So in the operational ROI, fewer detects, that is less rework, waste and downtime. Inline QC, that is reduces inspection times by up to 50% it will. And financial ROI is avoidance of product recalls. Aerospace, automotive recalls can cost 100 million plus. A faster throughput in the strategic ROI, early adapter advantage, premium pricing and differentiation, access to new markets, that is example, defense contracts, pharma regulatory compliance, and also in the risk ROI, reduces catastrophic failures, that is oil pipeline rupture. It will cost around 1 to 5 billion, including cleanup and lawsuits. So enhance compliance with ISO, FDA, FFA, and DOD regulations. So innovation ROI. So it will enable next gen manufacturing, that is smart factory industry 4.0. So in the summary, quantum sensing summary, quantum sensors uses a superposition, entanglement, and coherence to measure physical quantities with unprecedented precision. They outperform classical sensors in accuracy, sensitivity, and non-invasive defect detection. So, types of quantum sensors and principles, that is atomic clocks used for ultra precise timing, GPS, and telecommunication. So, quantum magnetometers detect tiny magnetic fields for brain imaging. Quantum gravimeters identify voids, density variations, oil 3D printing QC. Quantum gyroscopes, GPS free navigation. Quantum imaging, that is defect detection behind optical limits. Quantum thermometers, that is a nanoscale thermal mapping manufacturing medicine. So benefits of this one is non-destructive and ultra-precise inspections, real-time monitoring, and with less downtime, detects nano and micro defects invisible to classical methods, support predictive maintenance and Industry 4.0 integration. So, as we earlier stated, that the challenges in this quantum is high cost, so limited and large scale production, and also environmental sensitivity, that is noise and vibrations, integration issues with existing systems, skill gaps in workforce. and also lack of standards for industrial adoption. So, in respective to implementation strategies, start with pilot projects in high value sectors, hybrid adoption, that is quantum plus conventional entity, use AI and IoT, that is digital twins, to analyze sensor data, upskill workforce for quantum industry 4.0 skills, collaborate with startups, R&D, and other industries. Market trends and future opportunities, a current focus, that is defense, aerospace, and semiconductors, emerging users, manufacturing, QC, energy, healthcare, and telecom. Market growth is estimated is around 400 million in the year 2025. But in the year 2035, the expected is 3 to 5 billion, with the CAGR of 25 to 30%. Opportunities is, it's a GPS free navigation, quantum enhanced medical imaging, inline QC for smart factories, energy exploration, and infrastructure monitoring. So, in the quantum sensors are transforming manufacturing, materials testing, and quality control by providing precision, non-invasive, real-time insights, while challenges remain in cost, scalability, and integration. Their ROI and strategic impact are strongest in safety critical and high value industries like aerospace, semiconductors, and defense. So, over the next decade, as devices become smaller, cheaper, and AI integrated, quantum sensing will be a core pillar of Industry 4.0 and smart manufacturing ecosystems. Yeah, that's all for my side. Any questions?
Okay, if anyone has questions, please raise your hands so we will unmute you. If any question is there, please raise your hands so we can easy to unmute you. If anyone has any question, please ask. Raise your hands. Okay, I think there's no questions from the participant. Okay, thank you, Mr. Raguraj, for the wonderful session on the quantum sensors. We understood how they are bring high precision in monitoring quality control and predictive maintenance in the smart manufacturing. This talk as truly shows us how quantum technology is shaping the future of industries. Once again, thank you, Raguraj.
Yeah, thank
Thank
you.
you so
Thank you.
much. Okay, before we conclude the today's sessions, let me share the general criteria to receive the certificate. First is you must have a minimum 80% of attendance during the FDP. Attendance is tracked in each section. Daily session-wise feedback forms must be filled. And most important thing is participants are required to score a minimum of 60 marks in the quiz that will be shared on last day. That is called day 6. So finally, you have to maintain 80% of attendance, feedback submissions, and then whatever the assessment will be there, you have to score minimum 60 marks. Then only you are possible to get the certificate. Otherwise, you are not getting the certificate. So all the participants are requested to fill the feedback as well as the attendance daily without fail. Okay, once again, thank you all for your active participation in today's session. With this, we come to the end of our program. Wishing you all the pleasant evening and good night. Take care. Bye bye. Chetan, shall we conclude? Shall we log
So
out?
conclude, Modi, sir. Conclude, Modi.
Okay. Okay, all the participants, take care. Bye bye. Good night. We will meet tomorrow. One more sessions, one more resources person, and we are going to gain a more knowledge related to the quantum theory. Okay. Thank you. Take care. Bye bye.
So the participant session will be on another 5 minutes. If anyone has not yet filled the attendance as well as feedback, kindly fill it fast. So another 5 minutes session will be there. Afterwards, we're going to wind up session. Dear participant, we're going to wind up the session by 8:30. So another 5 more minutes is there. If anyone not yet filled the attendance as well as feedback, kindly do it fast.
Chetan sir. Hello, Chetan sir.